Good evening, ladies and gentlemen, and welcome to the Royal Aeronautical Society Space Group lecture entitled Infrared Eyes on the Universe, given by Dr. Zurbuchen. My name is Howard Nye. I am the chair of the Space Group at the Society. I was, until May, the president of the Royal Aeronautical Society. I'm now the immediate past president. I'd just like to say a few things about housekeeping. There will not be a fire alarm this evening in the building, so if the alarm does go off, we ask you please to leave the building. There's an exit here, or you could leave from the way you came in just now. The designated assembly point is actually past the hotel and at the junction of Hamilton Place and Piccadilly, so you'll just be on the Intercontinental Hotel. If you have mobility or access issues, please make yourself known to a member of the event staff so that they can make some necessary arrangements to help you get out. And please switch off your mobile phones. I must say I have mine on because I'm going to receive some mails potentially, but if you could switch off your mobile phones so they don't ring during the event. It is being streamed to our virtual audience. We're very happy to see all you here in person today, but we also have a large online audience, and they will be seeing it online, and it is being recorded so that you'll be able to see, everyone who's registered for this event will be able to see it online on the Royal Aeronautical Society YouTube channel. I should just say a little word about the Royal Aeronautical Society. It is a learned society. It was founded more than 150 years ago. It is the oldest society related to aerospace, aviation, and space. We have around 23,000 members around the world. We have approximately 60 divisions and branches. 2 are in the States. And we also are a registered charity. The patron of our charity is Her Majesty the Queen, so we are very happy. This, we give our personal views to government and so forth. We are an independent body, therefore we express our views in an independent view without any independent way, without any bias, which is very, very important going forward. I just would like to say that the lecture will close at 7 o'clock, and the first thing we will do is to have a short word from our sponsor, Telespazio UK. So if you'd like to play that for us on the screen. Thank you very much.
Hello, I'm Jeff Buswell, Head of Sales and Marketing at Telespazio UK, and also Vice Chair of the Space Group here at the Royal Aeronautical Society. It's really great to have the in-person Society lectures back up and running again, and what a way to kickstart them, with the James Webb Space Telescope being one of the world's truly great scientific programs, which can help us understand how the first stars and galaxies formed. It's a pleasure for Telespazio UK to be able to support such an exciting lecture, and I'd like to thank NASA and Dr. Zurbuchen for being able to talk to you in person this evening. So who are Telespazio, and what is our involvement in the James Webb Space Telescope? Well, Telespazio are a global leader in space systems and services with 3,000 people working across Europe and Latin America. Our systems support some of the major usage of space technology. For example, in monitoring climate change, where observations from satellites help us measure the changing level of our oceans and the greenhouse gases in our atmosphere. In monitoring critical infrastructure, such as rail networks or dams, where, incredibly, radar observations from space can detect subsidence activity at the millimetric level. Or in leading work with the European Space Agency on how to put in place communications and navigation services to support robotic and human activities on the moon. With the James Webb Space Telescope, then many of you will know that it's a partnership between NASA, the European Space Agency, and the Canadian Space Agency. At the European Space Agency's Astronomy Centre near Madrid, then members of the Telespazio team are involved in the development of the scientific archives, which hold all of ESA's astronomy data. This is now including data from James Webb, where we have a specific staff member who is liaising between ESA and the JWST scientific community to guide the software development of the European JWST archive. This work is very important because the archives need to easily be able to support scientists in searching, retrieving, visualizing, and interrogating the data in the optimal way, so the best science can be performed to enable the incredible discoveries we all want. I'd also like to reflect from a personal standpoint in that I worked at the Space Telescope Science Institute in Baltimore for a few months back in 1998 when I was a student. The Institute has been responsible for science operations of the Hubble Space Telescope since its launch in 1990 and is now responsible for the science and mission operations of the James Webb Space Telescope. When I was there, it wasn't called the James Webb and was a future mission called the Next Generation Space Telescope. At that time, it was scheduled for launch in 2007, so I think that gives you some idea of the incredible engineering challenges that have had to be overcome in order to now realise the truly revolutionary science that is expected with the telescope finally in space. I won't say any more as you have the key expert with you to explain all. Thank you again to NASA and Dr. Zurbuchen, and I really hope you all enjoy the lecture.
So thank you for Telespazio for sponsoring this event. I would like now to introduce Paul Bate, who is the Chief Executive of the UK Space Agency. He'd like to just say a short word if you'd like to come up. Thank you.
Good evening, everybody. There's really only two things I want to say. The first thing is, a job like mine is a great honour and is a privilege, but there are just moments when you realise that what you're part of, what you're a tiny part of. And this evening, as we hear about James Webb, is really one of those moments. For the agency, it is something very special. So we only seek to do three things in the UK Space Agency. That's bring in a lot more money to catalyse investment for the UK space sector. It's to deliver the missions and capabilities that matter most to the world and to the UK within it, and to champion space for its power to benefit people down on Earth. And there really isn't a better example of that writ large in James Webb. For those of you who follow the blogs, you clearly have an interest, otherwise you wouldn't be here tonight, and you hear so much more from Thomas. It is a generation-defining telescope. It's an awesome piece of machinery, and particularly within that, one of the four instruments, MIRI, the mid-infrared instrument, is a UK-led Gillian Wright as the co-PI, extraordinary piece of collaboration across 14 different universities and companies just within the UK. The images that are now available, I'm pretty sure you'll be seeing some tonight, just show the incredible improvement in resolution as we look back into the very earliest stages of the universe, the first light from stars, and of course the exoplanet search that's to come. So as we look forward to that in the summer and beyond, I hope you'll remember this is something that not only brings in great interest and excitement into the UK space sector as well as around the world, but it's a defining mission for us all, and perhaps most importantly, it is truly, truly inspirational. So thank you for joining tonight, and I'll pass back to Howard and to Thomas.
Thank you very much, Paul, for being here. I'd now like to introduce our speaker, Dr. Thomas Zurbuchen, the Associate Administrator in the NASA Science Mission Directorate. He is tasked with helping us answer some of humanity's biggest questions. Where do we come from? Are we alone? How does the universe work? Dr. Zurbuchen is well versed in the practice of asking difficult questions that help us to seek interconnected answers leading to real-world impacts. He is keenly interested in innovation and how leadership is developed and how the pursuit of excellence can help change the world. On a daily basis, Dr. Zurbuchen works to ensure that NASA's science missions build partnerships across disciplines and with industry and other nations to generate new questions and help advance the frontiers of knowledge and exploration. So I think, having said that, Dr. Zurbuchen, I would welcome you to come up to speak. Thank you.
It's going to be a test. Microphone works, is that okay? Look, it's a huge honor for me to be here in this esteemed community, in this location. It's great to tell a story of so many individuals, some of them in the UK, some of them in Canada, some of them all over Europe, and many of them, of course, in the United States. And I just want to tell you, I'm not going to really tell you the story the best way they could all tell you the story. But what I want to do tonight is really tell you two stories and interweave them. The first one is the story that is incredibly important, which is the one about exploration of our universe. There are very few things that are more important than for us to understand nature, to look at nature, appreciate that, because as we look at nature, we understand ourselves better, our place in the universe. And there's almost nothing more noble in my belief, and I think the history of this country and so many other places show that, than exploring, and also as part of that, moving the boundaries of ignorance and enhancing the space in which we both live and think in. That's one story I want to tell you about. And Webb, of course, is an important part of that. The second one is one that's a lot less important. It's small. It's kind of my view as the head of science of kind of how this telescope came together to where it is right now. I just want to tell you right now where we are. This week that we just started yesterday is the first time we're starting to accumulate long exposures of these instruments that are up there. We're still actually calibrating some of the science modes of these instruments. And you should know that when we launched, from the beginning, we told you it's going to take so and so many days. These days kind of are going to the end of June. Just within days of that, within a couple of weeks of that, we will, of course, tell you and show you the best data that has ever been shown of the universe in this kind of wavelength range. So I have to disappoint you right now. I don't have those data here today because we haven't taken them yet. We're taking them, as I said, this month that we're starting here in just a week. So that's where we're at, and that's the stories I'm going to tell you about. To start the first story, I want to go back and, of course, recognize that the exploration of nature is not something that is recent. It's something that started, in many cases, in ancient texts. This is one of my favorites. Lucretius, before Christ, kind of really out there talking about, frankly, ideas that are revolutionary and, frankly, were forgotten for almost 1,400 years after that, until they were rediscovered. No single thing abides, but all things flow, fragment to fragment, things just grow until we know and name them by degrees. They melt and are no more the things we know. The recognition that single pieces of knowledge by themselves, as we look at them from a scientific perspective, start coming together and creating new layers of understanding of our nature, new layers of understanding of our universe in a way that any one of them cannot. Chris, of course, talked about, frankly, something that many people talk about, precursors of understanding atoms, and kind of really in that analysis. One of the reasons I want to go back so much is to recognize that really the story of exploration is one for the generations, one for the centuries. And yes, I wish we would have launched the telescope a lot earlier than we did, but I just want to tell you we're in a line of so many observations that are there. If you ask about the beginning of the universe, this is what I would call the birth picture. It's a birth picture of the universe, really the background radiation, in this case by COBE. There's European Space Agency missions that are in many ways just as great or even better than this one. As I got help from John Mather, who is the Nobel Prize winning scientist, of course, who got some of his recognitions from this. You can see kind of the leaning more of the US missions. What is shown in this picture, of course, is the overall small variations in space of the temperature of the background radiation and the scale of that. What, of course, the expert sees in that after pulling things together is that this plot alone talks about substantial key parameters, key quantities of the universe that it constrains, both the distribution, the spatial scale, the composition of that universe, what's in it to a large extent in that chart alone. For me, it's one of the most amazing charts of all of space exploration because of the fundamental truth that it talks about the universe overall. If I go back and take the next step and basically say what is kind of a moment where in and from space knowledge about our universe has fundamentally changed, I have to talk about the Hubble Space Telescope, another international mission, just like the James Webb Space Telescope, one that is too big for one country, that is too big for one continent, but requires humanity to come together to really get the maximum out of it. The Hubble Space Telescope, of course, has created an inventory of pictures and views of the universe that is so broad. I invite you to do that experiment that I sometimes do on airplanes. And I'm sure some of my neighbors wonder who this guy is. I basically turn around and say, hey, if you hear the word space, what's the image you see so often? It is a Hubble Space Telescope image. If you hear the word galaxy, what image do you see? And it's either Star Trek or one of the sci-fi things, or it is yet another Hubble Space Telescope image. And of course, the Hubble Space Telescope has provided the kind of the view that away from our galaxy to the many, many other galaxies, which of course is knowledge that we only learned in the previous century. The fact that it's not just one galaxy, that there's frankly that the sky is full of galaxies. Galaxies, by the way, that are full of mystery still. We only 2 weeks ago had that image of that black hole in the middle of ours that was done by an international consortium and has imaged that black hole, recognizing, of course, now that galaxies and black holes go together like hand and glove. There are fights about which one goes first. The standard model is it's the galaxy that comes first, the black hole comes afterwards. By the way, ahead of the galaxy is dark matter that comes first, a perturbation in dark matter coming from that overall perturbation from that beautiful Kobe chart that is kind of imprinted after the initial Big Bang. And we're learning about this. The most important picture, though, and one of the pictures that have really changed how we're looking at the universe is the ultra-deep field, which is looking at somewhere near the North Pole for about 11 days of total exposure and just staring into a dark part of sky. For me, I'm still amazed about this. I think of it often when I talk to children about looking through a straw, roughly, a straw that you might pick up in one of those ice cream places, or and looking into the darkest part of the sky that you could do. What is shown there is a richness of frankly, an enormous amount of galaxies that are there, thousands of them, the likes of which, of course, are rich overall, some of them small, some of them big. By the way, we recognize that the vast majority of them have black holes in them. And the vast majority of them, of course, have kind of characteristics that are rather similar to some of the galaxies in our neighborhood. Those galaxies, of course, and everything we learn about them have a limit because the overall Hubble Space Telescope that has been built in the ultraviolet and just a little bit into the IR because it was orbiting or is orbiting Earth over 30 years of successful mission. Is stopping the view deeper into the universe. Of course, the reason for that. As the universe expands, the farther you look back in time, the more red the radiation gets. The more towards the infrared that the radiation is. And so basically for Hubble, it disappears because it can no longer be seen. And so for us, the question is, think of it like an album. I'm a little bit over 50 years old. The album that, the first birth album is kind of kind of a little kid with a really red head. Apparently somebody had to beat me to cry, my mother said. So that picture. And imagine the next picture is one where I'm something like 5, 6, 7 years old, and nothing is known in the middle. Now, take my life and put it into the universe. That's where we are right now. So what we'd really like to learn is everything from between after that kind of first cry of the universe until the kind of modern, much more modern universe, Hubble style, that we have not seen. That is what motivated scientists from all over the world to come up with an idea that had two characteristics that were really important. The first one is it had to be cold. The second one, it had to be big. It had to be cold because of the fact that I already mentioned that all these initial galaxies, the first generation galaxies, the first stars, were so old that their redshift out of the universe moved them to a place where, frankly, if we build it like Hubble, the heat of Hubble itself would flood it. And you could not see what, in fact, was the signal, the faint signal from deep space. It had to be big because of the fact that they're so far away that we wanted to have enough of the collection area to actually get that overall light focused down so we could, in fact, image and have a chance to actually see those initial stars and galaxies imaged for the first time. Now, of course, the moment you say cold, the moment you say big, you realize you need to go to space, and none of this fits into any rocket. Frankly, the biggest fairing, the kind of tip of the rocket that was available kind of during the design of this was just a little bit over 4 meters and so forth. And the overall mirror itself is 6.5 meters, 21 feet for those who count that way. 6.5 meters does not fit in a fairing except if you fold it. But that's not the worst. It has to be cold. The only way you stay cold is, first of all, you stay away from the Earth a long ways. And you make sure that any and all radiation from the Earth is not hitting you, including the moon, which itself would heat the telescope up way too much. You want to build a sun shield that's roughly a protection factor that you put on your skin of more than 1 million, suppressing the solar radiation and the heat radiation from the sun. And from that, looking into the deep sky. That is what Webb is all about, and that's what we're doing. Before I move on, I just want to acknowledge that the recognition to put telescopes into space was really the brainchild of this one woman, Dr. Nancy Grace Roman, who was one of the first female PhD students at the University of Chicago. She wrote a book and talked about her story, and it's frankly heartbreaking to see what she had gone through, just kind of taking one after the other hurdle after the other hurdle. And of course, she, together with Lyman Spitzer and well as others, came up with ideas that led ultimately to Hubble. We're excited that later this decade we're going to launch another telescope, which is like 100 Hubbles in terms of field of view, with her name on it, and move it into the sky. Because as we look at Webb and we look at Hubble, we do that understanding that it would not happen without her in this history. What's great about science is that we're changing our opinions constantly. There is no one fact of science that is there because it's somehow sacred to us. I always say the way we believe in science, the reason we trust science, is we take any one science fact that somebody puts in front of us and we beat it up with a 2x4 over the head. We try to take it down. We try to attack it. We try every which way to rip it down, and it persists. That's when we start trusting. And that's what good science is about, is questioning everything and putting, in fact, overall, trust behind it as a result of that. We have changed tremendously how the universe is. I don't know whether you've ever done that class. My PhD studies in astrophysics, we're in the mid to late 90s. And it's a really good exercise. By the way, also, I could never decide what to do, so I also studied earth science. It's really great to take the lecture notes out and kind of see what we learned. And take a red pen and say, hey, this is different. Here's a few things, and frankly, I will not talk in all details about it. But one of the things we had learned in the classes that I had is for a given star, the likelihood to form a planet was of the order of 1% or less. I want to tell you now that every night you go outside and look at the stars in our own galaxy, be aware that for every star that you look at, there's at least one planet out there, probably more than one, because we have not really seen the whole series of planets. So what happened to be a pretty unlikely event to form planets is now one that is all over the place. The overall question, however, how complex chemicals occur, is another one of those. When I looked at the class notes in the late 90s and mid-90s, complex chemicals were not really being talked about because you could write to yourself kind of down an equation of how likely it would be through these multiple collisions of atoms to build these complex chemicals. Look at Rosetta, the amazing complex chemicals that they found in some of the most primitive material of our solar system. Look at the deep space analysis of complex chemicals, both in our galaxies and in certain molecular clouds. Look at what we found looking at other samples that we brought back from here, or meteorites that are here. Complex chemicals are all over the place. What we don't understand, though, is, frankly, how these things, the beginning of the universe that gave that overall picture, the Kobe picture I showed you there before, how that related to the quantum theory that surely at the beginning dominated everything. The physics of the smallest scales of our nature, which is very highly non-intuitive, and frankly, it gives you a headache if you think about it too much, except that's what you do for a living, you get used to it. So for us also, what we don't understand still is that transition from these complex chemicals to something that is truly lifelike. And frankly, we don't know. Frankly, there's a lot of work that happened to get us from this state to here in many different areas, including, frankly, in quantum mechanics, including information theory, including understanding nonlinear feedback loops and systems that has roots in disciplines that are very different than astrophysics. And they're part of our community now. And of course, the key thing that keeps us up at night, and frankly for me, it's so important that we actually created a key theme in all of NASA science focused on astrobiology is really about life itself, both in our solar system and of course beyond, in our galaxy and beyond. Also understanding, of course, the origin of life here on Earth in a kind of research that is happening right now. It's absolutely stunning. I mean, for me, something that I read a lot of these papers and I'm just excited. Also the extremophiles, kind of life occurring in areas you would have never guessed life could be, even here on Earth. So for us, really, the question about this, in this overall realm, comes Webb. So I already talked to you about kind of the progression of telescope. I want to talk to you now about the progression of science questions that this is going to be. And I already mentioned to you that the most important part of that is the recognition that we need to go ultra deep. And for us to answer that and really look at the first generation of galaxies, which is there. Now, you could say, who's coming up with these overall priorities and who's doing that? I want to tell you, I'm really relieved that that's not my job. I think it's super hard. So there's some science that I know pretty well, but not much. Kind of deep science, I did my PhD, wrote a couple hundred papers on specific topics of science. I'm in that particular area pretty well versed as to what the important questions are and what the less important questions are. Not as secure about that anymore as I used to be when I was younger, but nonetheless, I'm better there. The vast majority of the science that we do, it kind of goes beyond the expertise of any one person. And therefore, it's really important for us at NASA and kind of in the US government in general, we actually ask independent bodies, just like this society, to provide priorities that help us, in fact, prioritize science over science. And you look at the kind of 10-year reports that are out there, and you see that in 1972, I was 4 years old, Hubble was being prioritized. You see that Chandra, kind of the X-ray telescope, came 10 years later, and so forth. You move up here, and you see in the year 2001, Webb was in fact the highest priority that was prioritized. Not because nobody had worked on it before, but at that moment in time, it became the highest priority that we were working on. We're, of course, hoping to launch it earlier, and I'm going to talk a little bit about some of these kind of challenges that occurred. Many of these challenges are beyond the horizon of my experience. I only worked at NASA for nearly 6 years. So I saw kind of the end of this mission, which, as somebody said, took over 20 years to get there. We just got a decadal survey. I hope some of you astrophysicists have read it. This is a public document. And frankly, many of you are not astrophysicists should read it also, because it talks about the amazing telescopes we should build next. I'm not going to talk about those right now. Already mentioned that the way we do any mission is by building an excellent team. And I just want to tell you that what I'm not going to talk a lot about here is that important aspect of team. In fact, I'm going to talk about 30%, I believe, of what it takes to do a good mission, which is technology. 70% of building a great mission is building an excellent team. It's a team that has diversity of thought, diversity of all dimensions in them. A team that learns how to listen to each other and frankly listens to the points of views and the opinions that come from those of the team who are in some kind of traditional ranking order at a lower level in the organizational structure. Because those, it turns out, are way more important than to mission success than some of the people at the very top of the organizational structure that, of course, are there to set the culture so the right discussions happen. It is teams that make missions happen, and here a shout out to the team of 10,000 or so individuals who have personally involved their own best to make this mission, to bring it to the place where we are. I'm going to jump on the second story, which of course is telling you a little bit about the story overall. Just about when I joined NASA, this is about how Webb looked. Webb was in two places. There was a bus, the spacecraft with the sun shield, I'm going to show you in a minute, and there was a telescope that was built. Now, to get to this, there's already well over a decade of technology development. Frankly, what had to happen to get to this particular picture is that, together with the picture I'm going to show you later, is that 10 new technologies had to be developed from scratch, including how to build one of those mirror segments and how to control that mirror segment in a way that these 18 overall picture, kind of little honeycomb pieces of the mirror could be formed into a single mirror that was as powerful as if we launched it as a single monolith. That was the goal. And that's what had to be tested here. You see the secondary mirror is folded up. It's going to come down, of course, and collect the light that is coming off these 18 kind of honeycombs directly into the secondary mirror, and then down the middle, down the barrel, into the instruments with beam splitters and so forth. I remember kind of being there when it was assembled, and within the first weeks, frankly, we were excited. Within the first weeks, we were doing an acoustics test and a vibrational test. Now, those of you who have not worked in space travel and in space research, let me just tell you, those are the most agonizing things. So there's the thing, and it's roughly worth, in this case, $4 billion just sitting on top of a table, and you're shaking it, and it's fidgeting, and you really wonder whether anything is going to fall off. What didn't help is the first time I did a test like this of any one of my instruments, it came flying off and hit the wall and fell down. Apparently I did not tighten the screws as well as I should have. That's not the mistakes this team did. Everything looked really, really well. Of course, the Arianespace people, the launch people, were there and needed to make sure that the overall specifications on how we were shaking it were in fact consistent with this. Because frankly, what we had to do is show that this sensitive optics could survive the roughness of space. We were shipping it off to Texas, and we're putting it into a thermal vacuum chamber where two things had to occur. We had to make sure that, in fact, we could align the mirrors under thermal vacuum, and it could also survive the thermal variations that it would undergo as it went. What we didn't plan for is Hurricane Harvey that came that way. And so I want to tell you, the team, again, exceeded what anybody was expecting. I remember visiting them a few weeks afterwards, and they were showing me where they were living. So even though their own houses were in peril so often, their own families had to evacuate, they were hunkering down with the telescope and making sure that it was safe. It never knew that there was a hurricane on the outside. I remember we were getting really worried that we were running out of liquid nitrogen, and we were trying to figure out whether we could kind of helicopter it in with a big military helicopter, and at the end, just in time, a road opened so we could drive one in. That was the biggest challenge, but this was not an easy telescope. What happened, though, as we were focused on the mirror, frankly, I would say we lost focus to a certain extent onto the other complex system that I'm having you here look at, which is kind of a one-to-one prototype. But this is, of course, an area of a tennis court, 5 times over, little foil. Each one of these 5 foils have to have exact shape to make sure that the protection from the sun is in fact as high as it is. We were looking at the schedule overall. The telescope made a lot of progress, and frankly, what I figured out joining NASA in 2016, late 2016, that we had really struggled with this particular part. In fact, what we had done is every few months we made a mistake that took a few months, and it delayed us while we spent roughly $1 million per day to kind of keep building it. It was a big crisis because it put in question whether or not as a team we could actually build this. I'm saying that to point out that actually the key elements of these mistakes were at that very level, at the technicians that were working there. And make no mistake, I'm not blaming those technicians. That is not the way these mistakes go. Let me model how they go, because I've been in labs like that. The technician says, "Do you really want me to do this? This makes no sense." And somebody says, "Shut up and do it." That's how these mistakes happen. It's not that the technician doesn't ask, it's that people don't listen. And that's the team that we want to build, frankly, we had to learn the hard way. We finally got it together, got the telescope, you see, assembled, put on top of that sun shield, and made it, something like 3 years ago, all together, and then basically had to go through 2 full deployments and learning how to deploy. I have to tell you, looking at this, you see how the telescope is coming in and it's being set down. Again, heart-wrenching for many of us. You just really hope the crane works, and it did. But what we had to do is really show that these deployments absolutely worked, and each one of the steps absolutely worked. And frankly, we found mistakes, quite a number of them. And we went and chased each one of those mistakes down and actually developed solutions for it. What really helped me is understanding that as we went forward, none of the mistakes would lead to total mission failure, but would lead to degradation of the telescope. So I felt a little bit better. But as we were getting ready and kind of getting closer, we were really starting to recognize that, hey, look, we've done everything we can do. Frankly, I put a number of people in a room and basically said, did we do everything that we could have to make this mission a success? And I'm sure you have better things to do than reading blogs and press stories, but one of the things I really wanted to do just about that time, I basically wrote down a blog post that was really important to me, and that basically said, no matter what we did right now, with the best team we've ever had on this mission, my point was, and I'm quoting out of it, if you're not scared or even terrified as to what we're trying to do, you're not understanding what we're doing. And so of course, what we needed to do is actually ship it from Los Angeles to French Guiana. The European Space Agency rocket, the Ariane 5, was going to bring us to space. And I'm just going to tell you, I'm going to share the most terrifying minute of my life here with you. It's kind of interesting. I notice my pulse still goes up, even though I know it worked out fine. But we were kind of, when exactly the ship took off was actually secret. We did not tell people because we hope nobody wanted to be famous. By the way, this is Greg Robinson waving, the guy I put in charge after these crises. He's now one of the Times top 100 influential people, as announced last week. And we're just really excited for this. So here we were on top of the rocket, and I had come down. And frankly, I was in the rain kind of the day before. We had to wait on the 24th of December. And I was on a helicopter by the French troops there and looking at this rocket. And frankly, I was terrified. I had spent a lot of time writing 2 speeches. I was the rank highest NASA official at this on Christmas Day down there in French Guiana, together with our colleagues, Josef Faschbacher, my close friend and Director General of ESA, and of course Daniel Neuenschwander. I told one of the ministers in Switzerland, we solved a lot of problems on Webb in Bernese German, because he's the head of transportation, and also like me, from a small part of Switzerland where we speak that accent that we both speak. So we talk to each other all the time, and of course the company, Arianespace and CNES, which of course did important work. So I'll live with you the last minute of Webb on Earth as we go forward. I want to tell you, I had practiced both speeches the night before, and I tend to not sleep so well, it turns out, whether we land on Mars or launch James Webb. I sat next to Josef Faschbacher, and he said, thank God we don't do this every week, otherwise I wouldn't make it through a month. And I think he is right. I also have a new favorite word, which is nominal, as pronounced in French, which I can't do, apparently. This, by the way, is on Christmas Day. And you know that the workforce in French Guiana is unionized. And I went after the fact, I went and thanked everybody, and I said, thanks for working on Christmas Day. It was the first time they had done so in the history of this company. And I said, we did it for the team. The Americans who were here spent 3 months with us, and we were, in fact, ready to go ahead and put our time in so they can go celebrate with theirs. I don't know whether I muted it accidentally.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
Nominal, you hear?
Vehicle performance is nominal.
it was just a couple hours later where we saw this. Now I want to tell you, the only reason we have this movie footage is because of another problem we had as a collective team. We had actually issues that we solved together with Arianespace and with the European Space Agency. We had agreed to put a camera on there. So what you see in the next movie is the release of the James Webb Space Telescope of the upper stage of the rocket. Its release, of course, that was then followed up with the energy boost to an orbit 1 million miles, 1.5 million kilometers away from Earth. Now, we knew it's going to come out that way. We were hoping. What we didn't know is what you're going to see next. And what was so amazing, I was standing in a row of individuals who had worked on Webb from multiple agencies, and basically in 1 single second, everybody started crying. And I'll tell you when. See, it's floating away, just like we wanted to, and we had not expected to see what I'm going to show you, which is, when you're a spacecraft builder, the most important moment of the spacecraft. There it comes. Do you see the solar panel coming out? We did not expect to see that. We had done calculations. My team had said that is not expected, and just came out. Why did it happen, by the way? Because Arianespace delivered us so perfectly that the tip-off ratio was so good that we didn't have to do any corrections. And so basically the solar panels came out and it waved goodbye to the Earth one last time. This, of course, was the final step of a successful launch. That alone, if it didn't come out, would have been the end of that mission. And of course, what happens when you launch a rocket normally, 80% of the risk of that spacecraft is the launch and the first few operations, and then 20% is what's after. Not with Webb. 20% is the launch and 80% is what's next. So I want to talk you through that. Of course, what we wanted to do is go out to the L1, the L2 point, that is, which is, as I said, kind of a million miles or 1.5 million kilometers, kind of the opposite direction of the sun. So if you go look at midnight where the sun was at noon, that's where Webb is, roughly. And so we're out there, and what we had to do is now deploy this transformer, this mirror and everything, and actually do it. And I want to tell you, if there were one number that was on my mind, that's not on the slide, but I knew it by heart, 344 single point failures. Okay, a single point failure on a mission is a failure. If that one thing is not working, the whole mission is a failure. Landing on Mars is what we did in February before, has 90 single point failures in round numbers. So this one is 3 times harder. So single point failures had to work. Of course, what we had to do is deploy the mirrors. We also had to have the sensitivity, an enormous amount, to get us there, both with the background, so we could see faint objects, and frankly, an enormous amount of excitement. And just to make sure, for those of you who have asked, the sensitivities of Hubble and Webb compared here, you see kind of just around 1 micron, Hubble kind of stops, and and Webb, of course, extends way beyond that with various instruments. This is shown at this side, of course. MIRI is absolutely critical. What an amazing instrument that will really totally revolutionize how we look at the universe. I'm going to show you one MIRI image at the end here, just for you to see how successful this is. All the others are really much less sensitive. Again, these are the 4 instruments, and MIRI, of course, is your favorite, and rightly so. But there's, of course, others who are at the near-infrared and mid-infrared, including the overall fine guidance sensor by the Canadian Space Agency. So let's go back to deployments. 344 single-point failures, 178 release mechanisms by themselves that worked, and that started kind of a few hours into it. Now I want to tell you, I'm a strong believer that you test as you fly and fly as you test. So I did not have time to go to all rehearsals that team did there. So I was not going there personally during the release of everything, because if I wanted to be there, I would have to have been there in all of our deployments. And what I did is instead I went to Utah to hang out with my family. The most nerve-wracking kind of ski vacation I've ever taken, because I was constantly checking, of course, getting texts. And frankly, it went really pretty well. There was 2-3 things that were quite shocking. Do you see how I think what I'm going to do is just show it here. So what we did, you already saw the deployment of the solar panels that came out. That, of course, took 2 out of the 344 off the table. So you count down until you get to 0. I was there when we cut the last 5, the final deployment of the mirror. And so I want to tell you, kind of, as we deployed these 2 sun shields, one of the most nerve-wracking parts were just after this one. You see, you're going to see that the entire sun shield is in a wrapper, and we cut that wrapper open. And it turns out one of the sensors of that wrapper did not work. Now, the wrapper was wide open, but we didn't know. And we were worried that it wasn't, but immediately we saw the temperature dropping. And everybody went from super nervous to calm as this deployed. The other thing that happened in the deployment is when we took one arm out, the whole temperature distribution came a little bit unstable. So immediately the team put the other arm out in a 3rd shift that was not planned initially to get it out there. And finally, at the very end, after the secondary mirror was out, that last mirror segment deployment, I was there, with the team and congratulating the whole team, because the whole telescope, the whole 344 single-point failures had basically not occurred. Every one of those individual items had worked, and this kind of miracle of humanity is out there waiting for us. So you can say, why did it take 6 months? Sorry, why did it take from December to June? Yeah, just about 6 months. And the answer is it's all about temperature. To cool the telescope to the exact temperature that it needs to operate, you need to go smoothly. And you need to go in a way that does not create any temperature gradients across the entire telescope. And as we went forward, frankly, what we had to do is heat up some of the parts to make sure that they don't cool fast enough to actually create such tension, and especially stay away from that water band. We want to go through that really quickly to make sure that you're not depositing water. That, of course, is because we come from Earth, is somewhere there. You go through that really quickly. That's what we have, and we're down here. We're doing the final kind of instrument calibrations. You see Mary is one of the final ones, kind of just a couple of weeks ahead until it's fully ready. We're still doing overall testing of these instruments, and of course, as I said, late June, early July, we're getting ready to do the science measurements. The most important one we're going to do is what I already talked about all evening, which is to look way down in space, look way down in time. Now think about this. The light we're going to collect will have been propagating with the speed of light to hit the telescope for 13.5 billion years. Those are really, really old photons, if you want. The oldest photons ever collected. And then we will focus them down. This is the oldest galaxy or something like it on Hubble we have seen. You see it's kind of fuzzy. It's right at the hairy edge. What we're going to do is see way deeper. Frankly, there's a lot of questions about the first galaxies we could talk about. Really about the chicken and egg, which is the black holes and the galaxy formation. But also, of course, the other thing we're going to be able to do is really look at star formation. Now, what is demonstrated here is how you can look through dust by switching to IR. And you see kind of what happened. The foreground went away and disappeared as you switch to IR. We're going to see behind objects, and objects that we're familiar with Hubble, entirely new ways. And we're going to also look at our own solar system objects. Some of the best images of Europa that, of course, will be visited both by European spacecraft, but also by an American one, JWST and Clipper, will be investigated with that. I'm sure if there are eruptions of water coming through the ice of Europa, we're going to see it. We cannot, with Hubble, totally prove that they're there. We're just at the edge of what's possible. We're going to see it. And of course, one of the things that we're looking at today that was not there when Webb was proposed, even early on, even in the early 2000s, it was not that topic, which is to look at atmospheres of planets elsewhere in the galaxy and really look at the distribution of the emissions that is coming from these atmospheres. Of course, what we're seeking to see is whether these atmospheres are the environments that we believe life could arise in. So we have a lot of worlds to discover, a lot to see. I'm going to end with 2 or 3 just pictures so you see. First one is the proof that we're focused. So we focus the entire mirrors, everything. This is at the theoretical limit of what we can do. This is in 2 microns. Of course, the difference between astrophysicists and the ones just look at the image, everybody looks at the star. The astrophysicists look at the back. Do you see these galaxies there? This is 2,200 seconds at 2 microns. It already has the depth of the ultra-deep field of Hubble without even trying. This is a technology image. So we didn't put that in the press release. But the point is, it's incredible. This tool that we have up there is incredible. And here, of course, is your favorite instrument. This is what used to be the best resolve kind of IR image by Spitzer, and one of Mary from the same location. This is an engineering image. This is not yet the best, but look at this. Each one of those kind of bright features, which are blobs in Spitzer, have individual kind of character, have clouds next to them, and have signs behind them. Again, galaxies that are way deeper in the universe than the object before. All the instruments are working the way they should. All of them are focused to their maximum ability, and we're frankly ready to get started with science. And I hope as you go forward with your talk series, hopefully in a few months you'll have another talk that gives you now the second part of this amazing journey of discovery, both one that's historic in nature, but one that is entirely made by humans that have themselves flaws and have challenges, but can build teams that can do extraordinary things. And frankly, when I look at that, I get a lot of hope for many things, including in exploration. Thank you so much. Please do.
So, Dr. Zurbuchen, this is, I can only say, inspirational. Your talk is absolutely inspirational. I'd like to give the word to Professor Southwood because he would like just to say a small word of thanks.
Well, it's very hard to follow that. What a display. When one comes to asking a member of the public, what are the great astronomical observatories in space? I guarantee you should bet on the word Hubble emerging, but also James Webb. For me, James Webb always comes top. remarkably, just the engineering, conquering the unfolding of that mirror, I think in this country at least, and I'm sure in the United States and worldwide, grabbed the public imagination that science only comes from great engineering. We Europeans have every reason to feel very grateful to you and to NASA for the key parts given to Europe and the UK to participate, and to NASA for sticking to the engineering and the science goals, as you've described. The ESA near-spec spectrometer, the British-led MIRI instrument, are going to be critical in delivering the science. But lastly, I've got to add my personal gratitude. As the person who set up the Ariane launch, but whose successor had to pay for it. I mean, that was a major, I'm really grateful for the help in doing that, but I'd really like to thank NASA for the trust, the faith shown in European technology, in putting what is obviously the flagship and giving us such an important part in launching that flagship. So thank you, NASA, for the trust. And let's all look forward to the great science that is to come. And finally, I've got to say, I'm only put up here to thank Thomas for doing an extraordinary talk this evening. And so I will shut up and say thank you very much for taking us along on such an emotional engineering and scientific journey. Thank you, Thomas.
Really appreciate it. Thank you so much. Thanks. Appreciate it. Oh, I didn't know whether you want to do Q&A or whether I burned through the time.
I think we've
I burned through the time.
Yes, no problem.
I scared him. What's the question you would have asked? Don't worry about it.
I think this has been a wonderful presentation, inspirational. This is the word I can only use, inspirational. We've seen the challenges faced in putting in place this extraordinary telescope. This is absolutely amazing, and in partnership with so many different industries, different nations, different space agencies, and as you say, the technicians who actually have to do the work finally to get it right. And we are advancing now so we know everything is deployed, everything is in place, and all of the systems are up and running, and now we are looking at commissioning the various instruments to understand how they respond, and so that we can go into observation and then research into the data we're looking at. So that we're at the absolute stepping stone to the next phase of full understanding of the past of our universe. I really want to thank you, Dr. Zurbuchen, for making the effort to come along this far to talk to us today. You recall that we asked you to speak, I think it was in 2019, we first had the first discussion about you coming to London to speak. I think it's good that factually it's happening now, because we're seeing the results of the launch and the first phases of the deployments. We then had the government shut down, and then we had COVID. But thank you very much indeed. I can't say any more than that. And I thank everyone being here today. Thank you for coming, and please make sure that you look on our websites for the future events. I thank you, also the people following this event online. I'm sorry we couldn't actually have any of your questions, but everyone who is registered and taking part in this event will receive an email which will have a recording of the event, which will be put up on the Society YouTube channel. So once again, I thank you again. I can't thank you enough. And I hope that we'll see you again to perhaps hear some more of the interesting outcomes of the first part of the research. Thank you very much indeed.